Part A of this question, we're proving by induction that for all positive integers, the sum of r cubed is 1/4 n squared times n plus 1 squared. So step 1 of my induction process, with n being 1, I've focused on the left-hand side of this result, with n being 1. So that's the left-hand side, with n being 1. So it's the sum of 1 cubed, which is just 1. Then looking at the right-hand side of this equation with n being 1. So I've plugged 1 in there, plugged 1 in there. And 1 squared is 1, 2 squared is 4. So 1/4 times 1 times 4 is 1. And I have shown that the left-hand side and the right-hand side are equivalent for n is 1. So the result is true for n equals 1. I've then assumed that the result is true for n equals k. So I've just copied this result down and swapped the n for k. I now need to use this fact to try and prove that it's going to be true for k plus 1, the next number. So the sum from 1 to k plus 1 is going to be the same as the sum of the first k terms plus the k plus 1th term. The k plus 1th term is just me substituting k plus 1 in here. So k plus 1 cubed. Then I have used my assumption. My assumption was that the sum of k terms is 1/4 k squared times k plus 1 squared. So I've plugged that in here. Just swapping that for that. Then I've done some factorising. I factorised out a k plus 1 squared from both of these terms. And I've also factorised the quarter out as well. So just checking, this times the k squared is this. And then this times the 4k plus 1 is this. Because the quarter and the 4 would cancel out, and then I've just got the k plus 1 cubed. I've then just multiplied this bracket out here. And then this k squared plus 4k plus 4 is the same thing as k plus 2 all squared. But I have written that plus 2 as plus 1 plus 1. Just to make it super clear to the examiner that this result is true for k plus 1. If this is a k plus 1, if we're doing the sum of k plus 1 terms, then this would be k plus 1, which it is, and this would be k plus 1, which it is. So what I've just shown there is that if this is true, if the result is true for n equals k, then that means that this shows it must be true for n equals k plus 1. The next number, if it's true for one integer, it must be true for the integer after that. I have also shown that it is true for the first integer. And therefore, if it's true for the first integer, it must be true for the second integer, and therefore it must be true for the third integer, and so on and so on. It must be true for all positive integers. So that's part A of this question. Part B says we need to use the standard results for r squared and r to show that for all positive integers, the sum of 2r times r plus 1 is that result given there. So first thing I've done is I've just expanded those brackets. The 2r times the r is 2r squared. The 2r times the 1 is 2r. And then I've just split that sum up into 2 lots of r squared plus the sum of 2 lots of r. To allow me to use the standard results, the sum of r squared is this. The sum of r is this. Not forgetting the timesing by 2 for each of those. The 2 times 1/6 is 1/3. The 2 times 1/2 is just 1. Then I noticed that they've both got an n in them. They've both got an n plus 1 in them. And I've also decided to factorise 1/3 out as well, which leaves a 2n plus 1 in the bracket here, because this multiplied by this is this. And we also need a 3 here, because those two terms multiplied together, this times this, gives me this. Because the 1/3 times the 3 is the 1, and then we just have the n times n plus 1. The 2n plus 1 plus the 3 is 2n plus 4. And then I've just factorised 2 outside of that 2n plus 4. That 2 multiplies by the 1/3 to get 2/3. And the 2n plus 4 is now just the n plus 2. So that's the result for part B shown. Part C of this question says to hence show that n equals 1 is the only value of n that satisfies this equation. So the left-hand side of that equation, I've just copied down my result from part B. The right-hand side of the equation, we've got 4 times the result from part A. The 4 times 1/4 is just 1. So that gives me this equation here to solve. Now, considering that I know for a fact that n cannot equal 0, because it has to be a positive integer, because I know n can't be 0, I am allowed to divide both sides by n. On a similar logic, because I know n cannot be -1, because again it has to be a positive integer, because n can't be -1, I know I'm also going to be allowed to divide both sides by n minus 1. So that's what I've done. I've cancelled, I've cancelled this n with that, I've cancelled this with that, and that's got me to this line here. I've then just multiplied this side by 3 and multiplied those brackets out. And then I've multiplied the 2 times the n plus 2 here. It's a quadratic equation, so I've put everything over to the right-hand side. Factorised, this is a show that question, and found that the only solutions are n is -4/3, which is not allowed because it's not a positive integer. Therefore, n equals 1 is the only positive value to satisfy that equation.